Good afternoon, everyone. So today I'll be presenting a talk on Three Musketeers, Sherlock Holmes, Mathematics, and Julia. So just trying to relate different concepts from different domains to solve the uh, crime scenes or cases. So in today's talk, we are going to discuss what's a forensic investigation process, Dover standard and Julia, and real world problems like pressure of a shoe print on a soft ground and okay. So then digital forensics applications. So let us see the definition of forensic science. It's the use of scientific methods or expertise to investigate crimes or examine evidence that might be presented in a court of law. So that's the goal of forensic investigation process. So you have to present your findings as an evidence in the court of law. So for that, you have to follow the scientific methodology. You have to follow the procedure led by the code procedure led by the government. So if you don't follow the procedure, then your evidence will not be admitted in the court. Then here mathematics can be used to determine how crimes are committed, when they are committed, and who committed them. Then some of the mathematics concepts which can be used are measurements, trigonometry, proportions, handling data, probability, and distributions. Of course, the list is endless. It depends on what kind of crime you are solving. Then forensic scientists analyze the crime scene for possible clues pointing towards suspect and evidence. So we are going to use languages like Julia or Julia to find out the evidence. So some of the forensic applications are lie detection, determining the time since death, then accident, suicide or murder, then calculate the percentage of concentrations, then compute blood stain thickness, then ricochet analysis, and aspects of ballistics, DNA analysis, and fingerprint analysis. Of course, these are some of the examples. Then whenever we consider any forensic investigation process, so these are the 6 steps: identification, collection, validation, examination, preservation, and presentation. In the identification step, the investigation officer visits the crime scene location and tries to identify what are the objects he or she needs to take in his or her possession, because there can be some devices which may look like toys, for example toy USB, right? So those should not be left out. And if there's a computer or a laptop, its state needs to be preserved. If it is off, then investigation officer needs to carry the system in the same state. If it is on, then he or she needs to just pull the plug so that it can retain the state. Because if you restart the system or if you start the system, the information stored in volatile memory will be lost. So there is a order in which the information should be collected. Always the order is you have to collect least volatile information, the most volatile information first and least volatile information last, right? Then after that, you have to validate the data. So you can't perform analysis on the original data. You need to make a copy of it. So when we say copy of it, we are speaking about disk to disk copy, not the physical file copy or folder copy. So we have to create system image. So there were some tools like Norton Ghost. So of course there are some open source tools are also available which can help you to create the image of the entire system. Then next comes the examination. So in this step, actually, the investigation officer performs the analysis of the information, tries to find out the uh, pieces of evidences and tries to correlate these different pieces. Then next is the preservation. Preservation is also very, very important. So it has to be stored in a locker at appropriate temperature, and we have to ensure that no magnetic device or no other device is interfering with the evidence. If that happens, again the entire process has to be redone, and the most important thing is that the evidence will not be acceptable by the court. Then finally, the presentation. So this is most important because you are going to present your findings in the court of law. Then there's something called as double standard. So in United States federal law, the double standard is a rule of evidence regarding the admissibility of expert witness testimony. So a party may raise a Daubert motion. So it's a motion in limine raised before during trial to exclude the presentation of unqualified evidence to the jury. So there are some illustrative factors defined by the court, and they are part of scientific methodology. So those factors are: has the technique been tested in actual field conditions and not just in laboratory? Has the technique been subject to peer review and publication? What is the known or potential rate of error? Do standards exist for control of techniques operation? And has the technique been generally accepted within the relevant scientific community? So in 2003, Brian Carrier, he published a paper examined the rules of evidence standards, including the Daubert. And he compared and contrasted the open source and closed source forensic tools. And his conclusion was that using the guidelines of Daubert tests, we have shown that open source tools may more clearly and comprehensively meet the guidelines of requirements than would the closed source tools. So Julia is open source tool, Python is open source tool, and both are known as scientific computing languages. So no doubt, so Julia can be used here. And when we apply these rules to Julia language, then we have to ask the questions in a different manner here. So here we can ask like, can the program or algorithm be explained? So this explanation should also be in words, not only in code. Then has enough information been provided such that thorough tests can be developed to test the program? Then have the error rates been calculated and validated independently? Has the program been studied and peer reviewed? Has the program been generally accepted by the community? So Julia satisfies these illustrative factors. So it can be used for forensic purposes. So we'll see some real world problems. So such as pressure of a shoe print on a soft ground. Then we'll try to decide whether it's a suicide, murder, or accident. Then application of Pythagoras theorem, then resolution of human eye, then finally the bank account analysis. For many of the applications, just a simple formula will give you the result. Just 1 or 2 lines code is enough. So that's why I don't have programs for many of these applications here. For example, consider this one. So pressure of a shoe print on a soft ground. So you can see the image here. So measurements are taken of the length of the shoe prints and the depth and how far apart the prints are. So based on this, you can determine how taller the person is. So the taller the person, the longer the feet and the stride. And the bigger the person, the deeper the shoe print. Okay. So based on that, it gives you some idea regarding the suspect. So formula which you can use here is P equal to mg by A. So where g is approximately 10 meters per second square. So m is the body mass and A is the contact area with the surface. So the unit of measurement is in terms of pascals. So just a simple formula will give you the result. Just substitute the values and you will get the result. Then next is the suicide, accident, or a murder. So consider here there is a building and from that building one dead body has fallen, right? So based on the distance, right, based on the launch angle, you can decide whether it is a suicide, murder, or accidental fall. So there is something called as launch angle. So this launch angle is important indication. If launch angle is 0 degrees, then it is accidental fall. If it is suicide, then it is 21 to 38 degrees. If it is murder, then again it will be very low. Okay, so that is because there will be initial force which is applied to the body. So whenever someone jumps or whenever some someone throws the body. So for this, you can use this formula y is equal to h plus tan theta of x minus g by 2 raised to mu square cos square theta into x square. So these are all just single line formulas. You just need to substitute the values and you can determine you can get the result very easily. The next is the Pythagoras theorem, which is very famous, right? So all of you know it. So the square of hypotenuse is equal to the sum of the squares of the other two sides. So that is a square plus b square is equal to c square. So let's see how it can be used. So it can be used to detect artifact smuggling. For example, the authorities have video evidence of a possible suspect in the museum break-in. So the suspect was seen carrying a briefcase measuring 20-inch long by 16-inch high by 3-inch wide. So one of the artifacts stolen was 24-inch long and 2-inch wide. So investigators are trying to determine if this artifact was possibly smuggled out of the museum in this suspect's briefcase. So here the Pythagoras theorem can be applied to the dimension of the briefcase. So here we get it is as 20 square plus 16 square is equal to 656 and the square root of 656 is 25.6 inch. So the length represents the widest space of the briefcase. Since it is greater than the length of the artifact, it is conceivable that the artifact was smuggled out of the museum in the briefcase. The next is the resolution of a human eye. So generally what happens is it is used for identification of an individual in the court, right? So here consider an example of witness statement concerning the identification of an individual valid given that the suspect was some distance away at the time. So the fundamental result underlying this is that the unaided ideal human eye has the angular resolution limit of around 1 minute of arc, which is equivalent to 0.0003 radians. Then such resolution limit means that any two distinct features in an object that subtend to an angle greater than this will be resolvable by the eye. So otherwise features will merge and appear blurred and indistinct. So if a particular feature separated by dimension d lie at distance L from the observer, then by the definition of radian, we require the following condition to hold the object to be resolvable. That is d by L should be greater than 0.003 radians. So this is the problem here. So a witness with perfect eyesight who viewed the suspect from distance 200 meters in daylight claims that he was wearing the striped jumper with stripes being around 4 centimeter wide. So is this statement scientifically reasonable? So here the condition for the image resolution becomes and it gives the result as 0.0002 radians. The next, let's move to the digital forensics part where most of the programming is involved and we may have to write more longer and more lengthier programs here and apply more advanced concepts also. So first important concept is the hash functions. So why do we compute hash functions? We compute the hash functions to ensure that the integrity of the information is maintained. So if someone modifies the information, then the hash code will definitely change. For example, consider this. Here we have a message hello world and we have computed the hash code of hello world message and we have got some value. Now in the next example, what I have done is I have just added the extra space at the end of string hello world. So now you can notice here that the hash code changes. So even the small modification, if you alter the evidence, so it's going to give you the different hash code. So that's why whenever the investigation officers they create the disk image of the hard disk, first thing they do is they compute the hash code and store it somewhere. Then they create the copy of it and again for the copy also they compute the hash code. So both must match in all cases. So if there's a mismatch, then that's a proof that the evidence has been tampered. The next is the extracting metadata. So metadata is the information that is data about data. For example, if you have a file then we have information about a file. For example, when it is created, what's the size of the file, who created it, right? So when it was created and so on. So for this in Julia, you can make use of file IO package along with specific other packages for extracting image information, for extracting audio information, for extracting video information, for extracting document information. So consider this here. You have to install these packages, that is file IO, then image magic, audio IO, and CSV files. Then you can import these packages by saying using statement. So using file IO, using image magic, then using audio IO, and using CSV files. Then next, the first thing you have to do is you have to set the path for these different types of files. Right? Then load the file, then use the package and get the information. Right? For example, if you want to get the information about an image, you have taken a photo. So in that case, the GPS location of the photo becomes very, very important. So that information is very vital. Right? So similarly with respect to audio, you can get the information about the audio length, audio type, what's the bit rate, and so on. Then similarly with respect to CSV files. So these are just the examples, but this list can go on and you may have to work with specific packages to extract the information about the files. The next is forensic indexing and searching. Now, I have already explained that investigation officers, they make the image of the entire system, right? So that data will be in terms of gigabytes, right? So it is very difficult to search the information in that gigabytes of information. There will be thousands of files. So in that case, what you have to do is you have to build your own search engine for that particular data. So that is what we mean forensic indexing and searching. So we are looking for specific information in the image, right? So once we get that information, then we can try to find out the links. So in this case, you can perform forensic indexing and searching using the packages called as light graphs and metagraphs. So metagraphs is the advanced version where you can have information in terms of graph. So you can add any information to the vertex and you can have edges between these vertices. So you can create a metadata graph by adding the path here. So for example, you can see that there's a statement here, metadata is equal to dictionary. So dictionary key is defined as content, and that's the key, and the actual content is defined as the file content. You can also specify here the file path, and you are seeing here that we are adding it to the vertex. So likewise, we have to add all possible information which we want to index. Once the indexing is done, then we can go for search function. So you can write a function called as search evidence, which will basically does the graph search and gets you the matching vertices. The next is logging package in Julia. Logging is again one of the very, very important aspects in Julia, right? Not in Julia, in forensics. Okay. So what happens is that whenever you perform forensic analysis and when you present the evidence in the court of law, your opposition lawyer may also question it, right? So if you have logging package, if you are logging everything, right? So which file you have selected, what columns you have selected, right? How you have performed the search, which algorithm you have used, right? It has to record each and every step and create a document. So how it has done. So that if the opposition lawyer or if any other person, if he reproduces the results by following the steps mentioned, right, then that can be acceptable, right? If it gives different results each time, then it's going to be problematic and that evidence will not be accepted. So reproducibility is again very, very important aspect here. So this is how you can make use of logging package. So basically you can use it and you can insert these different types of messages at various places of the program so that it can record and it can print to a file, print to a log file what is happening. So then next is the bank account analysis. So this is a pressing problem, which I had also presented this as a lightning talk just half an hour ago. So in money laundering scenario, what happens is that, so there are three stages. One is placement, then layering, then the integration. So whatever money you get, so that will be divided into several small chunks and it will be deposited into several bank accounts. And at the end, it will be integrated and it will reach the intended recipient. So now you can see here that the arrows which are shown in red color, that depicts the money laundering scenario. The arrows which depicts in green color, that depicts the normal scenario. So basically we are going to follow this process. Investigation officers are going to collect the information from various banks, right? And all of these statements will be having different formats. So first task will be to get all these statements into unified format. So once you get it into unified format, you can filter these bank statements using Benford's law. So we'll see what is Benford's law. It's a first digit law or leading digit law. Basically, it's a distribution by which you can tell whether the money laundering has happened or no. Basically, again, it gives you just a hint. Then import the suspicious accounts. Here you can import the data of PEP, that is politically exposed persons, and relatives of politically exposed persons, and also the sanctions data. Then generate a graph showing the links between the accounts and the transactions. This is very, very important. Then apply machine learning on the above graph. Then predict the possible money laundering. Then also generate the chain of accounts with fraudulent transactions. But in all these steps, you have to record the steps because it is very, very important for evidence verification and validation. Okay, so this is the Benford's law. So it's also called as leading digit law or first digit law. So you can see here it shows what is the number of occurrence of each digit in the financial transactions. So 1 occurs at highest number of times, that is 30%, then 2 17%, 3 12%, 4 9%, and so on. So we have written a code in Julia, so which basically extracts the leading digits of credit and debit amount and plots them in the Benford's distribution. So now you can see here that there is a blue bar, so which is the actual amount, and red one is the expected one. So there is a lot of deviation in the first case itself. So that means that there is a possible money laundering here. Whereas consider this, now your red dots are more aligned to the blue bars. So that means there is no possible money laundering. Now when you read the accounts, right, so you also need to generate a graph which shows the relationship between different graphs. Now you can see here that in between some vertices there is a dark line, and between some vertices there is a blue line, light line, right? So that means what? Dark line means what? There have been more number of transactions between those accounts. There have been frequent transactions between those accounts. So that gives a indication that there may be a possible money laundering scenario there. Then in conclusion, so forensic investigation is a highly scientific process. So since Julia is scientific computing language and conforms to Dober standard, it is one of the most suitable languages for developing forensic tools. And in forensics, accuracy of clues and evidence matters rather than the performance of the application. Thank you.
Hello, thank you for the presentation. I have a question about Benford's law. I know that many government institutions, although they don't admit it, they use Benford's law to detect like tax returns, frauds, and things like that. Do you guys have some kind of metric to detect how much of a possibility of fraud is happening when you look at this graph? Because you could also just take a look and visually try to decide if there is a possibility of a fraud or not. But you guys have some kind of metric to numerically decide if there is a possibility of fraud or not.
Yeah. Correct. So Benford's law is just one indicative tool. It doesn't mean that it just follows the Benford's law distribution. It doesn't mean that there is a possible money laundering or there is no possible money laundering. So it has to be combined with more specific machine learning algorithms and determine whether it is money laundering or no. So it just gives you some indications. So generally what happens is the investigation officers, they need this data for various purposes. For example, whenever they are analyzing the bank statements, they want to know how much amount has been credited, how much amount has been debited in during over a period of time, right? How much money has been debited from the ATM, how much money the person has spent over POS, right? How much money he has uh, withdrawn from the ATM, right? And they will also see what is his regular income and what is the match or mismatch, right? So it is just one indication tools. Yeah.
Okay. I have another question. Do we have time? I imagine that you're coding most of your things, your tools in Julia, right? And do you guys have to submit the code as an auditing procedure for the code when you guys are, I don't know, giving testimony?
Yeah, we can submit. That's not a problem.
But is it required? Not necessarily, right? Okay.
Yeah.
Thank you.
All right. Do we have any other question? Yeah, back there.
So I saw in your list of examples you included ballistic analysis and list of examples mathematics can be used for. I know recently there's been news of ballistic matching to a certain gun being declared like a sort of junk science, and Maryland Supreme Court that you can't match a bullet to being fired from a specific gun due to manufacturing tolerances would be over the whole batch. Do you have any comments about that, or is that not really in your field?
No, I don't have any comments.
All right. Does anybody else has a question? If not, we can take our speaker, and this is the end of our morning session.